Okay, going to switch over to some geometry here, and we're going to talk about some conditions that for proofs. So we have a conditional statement in this first lesson that we're going to talk about, and the conditional or constructing arguments. You can see some examples there, the vocabulary on the left. We're going to focus on a couple of those vocabs. The first thing is if you have a conditional, that's an if-then statement. The if part being the hypothesis and the then part being the conclusion. If you have an example here, a triangle with all angles congruent is equilateral. So that would be if you have a triangle, all angles, you can abbreviate how you want for me. Some people are probably a little more particular about that. All angles congruent, then the arrow notation, you can write the words if and then if you want. I like the arrow notation. Then it is an equilateral triangle. Hypothesis, conclusion. All right, the second one, Alberto can go to the movies if he washes his car. So Alberto washes car. Then he can go to movies. Doesn't see he will or he has to, but he can. All right, so that's just, when we're doing proofs, you have to base everything off from these facts. Okay, now the next thing, this one, a lot of times you'll see problems or tests sort of questions. So you've got your hypothesis, your if then. A converse, so here's my if P then Q. The converse right here, your converse is going to be when you flip those around. Turn it to, and that will not always be true. A negation is when you say not P, and then when you do an inverse, you say not P, then not Q. Again, not always true if you have this conditional to start with. I'll give you an example here. And then this one's not always true. This one will always have to be true. So let me give you my example, that my favorite to use. Okay, so assuming we're outside and there's a sidewalk, nothing obstructing it from the sky. If it's raining, then sidewalk is wet. Okay, so come back up here. Talk about the converse. Remember, that's where you flip it around. So if the sidewalk's wet, does that mean it had to be raining? Well, it could have been a sprinkler, it could have been something else. So no. So again, that's my example for no there. And then come down here to the inverse. If it's not raining, then the sidewalk is not wet. Well, again, it could have been wet from a sprinkler, from somebody spilling. So those two, they are not always true. However, let's take a look at the contrapositive here. The contrapositive. If the sidewalk is not wet, if it's not wet, and remember I said there's no obstruction to the sky, then it's not raining. And then when you do not, it's like this little tilde in front of it. So not wet sidewalk, then not raining. And that would have to be true. So the contrapositive is always true. These inverses and converses sometimes are, and it's all based off from the fact that to start with, your hypothesis conditional statement was true to begin with. All right, so that's for proofs, it's all based off from using these logical reasonings. We could talk about more examples. There's this chart here that summarizes everything we just talked about. But let's go ahead and continue to the deductive reasoning. So in deductive reasoning, again, it's all based on logical thoughts and connections. These two, sometimes you'll run into test questions about these two things, law of detachment and law of syllogism. The deductive reasoning of it just means it's all based, it's a process, here you go, a process of reasoning using given and previously known facts to reach a logical conclusion. So it's all connected. I always say this type of reasoning is like a lawyer, an attorney, that when they build a case, it needs to be airtight. So the law of detachment says this: if P then Q, your conditional statement, if that's true and P is true, then it has to follow that Q is true. So this is kind of just, to me, it's like you just have two things involved. If P, then Q. As long as P is true, Q has to be true. That's just like the basics, law of detachment. Now, law of syllogism, you're going to put things together. So you start with your P, then Q, and then you go on and you say Q, then R. This is like my condition. If these two things, then it follows that P leads to Q, Q leads to R, that P goes directly to R being true as well. And so that's law of syllogism. And notice the difference here is you have three things involved. It's kind of an indirect way to get from P to R. You have to go through Q. All right, so Martin walks his dog before dinner every day. Martin's now eating his dinner. Use the law of detachment and syllogism. All right, so it says he walks his dog before dinner. He's having dinner. So if Martin is having dinner, then he had to have already walked his dog, right? So it's like in order to get to walked dog, you had to go through the idea that he did dinner, okay? So moving on. And so anyway, basically those are the two things in this lesson that you might have to use. Let's jump over, let me switch screens here to the next two lessons that are in there. 1-7, 1-8 from the Savas Geometry and Vision. Let me double check that I get you the right screen here. And in here, we're going to start talking about actually what does most books, there's some different ways of doing proofs. Some of them do them as a paragraph, you see here. You see this is the more formal, normally what people think of, called a two-column proof, your statement on the left, the reason that justifies each statement you're making on the right. And then sometimes you'll actually see a flowchart proof. But anyway, that's just the format of it. And we're going to get into those more later. So I'm just going to say you've got your vertical angles and you've got your linear pairs and your supplementary angles, complementary angles sometimes. And then we get into just 1-8. That's going to be what's called an indirect proof. You're going to get to the proof, but you're going to go through assuming or showing that if something doesn't happen, then the other thing can't happen. And so a contrapositive, we talked about that at the beginning. If P then Q, if that has to be true, then not Q means not P. And so if you can prove this one, because it's the contrapositive, and the contrapositive is always true, then that would have to be true. So by contrapositive, we're going to kind of, sometimes they'll say you're going about the proof going through the back door instead of through going from the things you know to get to what you want to know. Indirect proof, again, you're going to go about doing it through either a contradiction. If you show something, what you want to, if you want to prove if P then Q, then start by saying, well, what if it's not Q? Then you go on to say, well, if it's not Q, then P can never be true. And so by getting to that point, that's an indirect. It wasn't going the forward direction. It's almost like you went in reverse. So those are the basics of the lesson. I think you'll get it if we start showing how it works with actual problems. So there you go.